Okay, so let us, we were talking last time about a splitting field. So suppose we have a polynomial, um, a splitting field. For polynomial f of x over k. Is a field we call E. If it exists, which it will, but I'm acknowledging at this point we haven't shown that such an animal exists, such that f of x is f is a product of linear factors over the. So in particular, all of these alphas must be in E, right? Because all these linear factors are there. And I think it's more as economical possible. So this can be very dependent on which phase. So for example, what's the splitting field for this? Well, it depends on what my base field is. Splitting field here is Qi, which is a degree 2 extension of the interactions. X squared plus 1 doesn't have any roots in Q squared root of 2 because this is actually subfield real. So let me be more dramatic. Splitting field for this over reals is this. X squared plus 1 already splits into linear factors over C. And over Z2 it's Z2 because so it already splits into linear factors here. Over Z5, X plus 1 is actually X plus 2 times X minus 2 over Z5 because minus 4 is equivalent to 1 minus 5, so it splits. What about over Z3? If you look at X squared plus 1, the good thing about quadratics and cubics is they're irreducible if and only if they don't have a root, right? over Z3, plug in 0, and you get 1, plug in 1 and you get 2, plug in 2 and you get 2, right? So no roots here. So the splitting field here would actually be like the ideal one, which is, this is actually a field of 9 elements. We're going to talk about this later. So splitting fields are, for a polynomial, if they exist, are it's a field where the polynomial factors into linear factors, and it's as small as possible over the base field where it splits. You can define a splitting field of, you might try to find a splitting field of multiple polynomials, right? Like one where x squared plus 1 and x squared minus 2 both split. Notice that if you have any finite collection of polynomials, it's the splitting field of one polynomial. Because all you got to do is take the finite number of polynomials and multiply them. Right? So let me get around this in the next theorem. Splitting fields do exist. And I'll be more precise in this theorem. Suppose we have a field let's say the field and say that of degree n greater than 1. Then there's a splitting field of f, but there's a splitting field of f such that d by bound degree what's in it? Yes. I wish. So here's what could go wrong. So let me kind of talk you through it. Suppose you have rationals and I give you a 5th degree polynomial, right? You want to find a splitting field where you get all the roots. Well, so you pull a root out of that polynomial and stick it on the cube. That's a degree 5 extension if the polynomial is irreducible, right? Now what happens? Well, in this new field, you've now got a factor of x minus that root times a 4th degree polynomial. Now, if that polynomial is irreducible, you've got to pull another root out of it and adjoin it. And now you go 5, 4 in a worst case scenario. So n factorial is a worst case scenario. Sometimes sometimes it'll be better, depending on your situation. So proceed by induction on if n equals 1, this is clear. Because if the polynomial has degree 1, that means that it already splits in k of x. And so the splitting field should just be the field of k itself, which is degree 1, which is one factor. Right? We will assume that if f has a degree not exceeding n minus 1, then there's a splitting field of no more than n minus 1. So, for my inductive hypothesis, suppose if degree f is less than one, then there exists a splitting field such that degree of f of k no more than n minus one. Right? Now, let's assume that the degree of f is n. We want to show that there's a splitting field of degree no more than n factorial over this. Suppose we have an irreducible factor of f degree more than one. That's an irreducible factor. Degree more. That is to say, notice, of course, that the degree of f is n, and n has the factor, right. So, of course, now my inductive hypothesis that n is at least 2. So this thing has to have a irreducible factor of degree 1, or degree more than. Oh, no, it doesn't. It can factor in linears. So yeah, so let's just assume that we have this situation. So actually, like this note here. Note if all irreducible factors of f(x) have degree 1, what can we conclude then? Right, we can conclude the polynomial already splits in the base field K. And the degree of K for K is 1, which is less than or equal to n factorial. So if we have an irreducible, if all the irreducible factors are of degree 1, then that means the polynomial already splits and the theorem quite easily holds. So let's suppose that we have a factor that's irreducible of greater degree. Let U be a root of G. And there's an extension field, K, in which G has this root U. So this extension field has degree G, that's the degree of the extension of KU over K. And so what we know that in KU, we have one root of G, and G, of course, is a factor of F. So F has this factor of X minus U that I can pull out right here. And degree of H is n minus one, which will allow for our inductive hypothesis. So by induction, there exists a splitting field for H of X over KU and such that three of F over KU is less than or equal to N. So the degree, so notice N F F of X splits. Because F of X is just this linear polynomial times this thing of degree N minus one. And the splitting field F, this thing splits into linear factors. This other piece is already linear. And the degree of F over K is the degree of F KU KU K, which is less than or equal to N minus one factorial times 3 of G, which is in. And that's that. Now, there's one thing that I should have, my inductive hypothesis. I should have taken K to be any field. Right, not just K, because I needed to apply the inductive hypothesis to K here. But that's a minor change. Okay, any questions? So let me give you a couple of examples that you might play around with. Mess with here. This one's splitting field. That is a splitting field. This is actually we work this example, right, which is much less than 4 factorial. Like worst case scenario by the previous theorem, splitting field might say 24 extension, but what happens here is your dream comes true. It turns out that when you adjoin any root, you get algebraics for this. If you look at x cubed minus 2 over q, the splitting field here adjoining the cube root wasn't good enough. You had to do more stuff. Yes, this one. This one's got a worst case scenario of 5 factorial. This one I will stay without proof, because you'll prove it for me later. This one's 20. Okay, so I mentioned this word, at our last meeting. Now we'll formally define it, or formally that is, or anyway, definition, 833. We say that F is a normal extension of K. Okay, so what does it mean to be normal? If every non-constant irreducible polynomial polynomial let me say KX. Splits. So we say that an extension is normal if every non-constant irreducible polynomial of K of X that has a root F actually splits over F. And we'll assume here F is algebraic. If you remove the algebraic assumption, everybody knows a normal extension of Q. If you just take the definition before my parenthetical mark, and that is complex numbers, right? Because every polynomial with coefficients in Q that has a root in complex numbers actually splits in complex numbers. In fact, any polynomial over the complex number period actually has a root and hence completely splits in complex numbers. So I mentioned this earlier in the following context. I gave you this kind of buzzwords here, and Galois, which we're now more familiar with, is equivalent to actually normal and separable for algebraic extensions. I have not defined separable yet. We'll get to that soon. But I want to point out that being a separable extension is kind of a technical thing, and in characteristic 0, all fields are separable. And so here's another way to think about this, which we will get to. A field is normal over K, if and only if it is the splitting field of the set of polynomials. So these splitting fields, that is fields that you would join all the roots of the polynomial to, these things are automatically what we call normal. How many of you have heard the term algebraically closed? If you like algebraic geometry, you will hear this. Lots of theorems that they do, they need something like the field to be algebraically closed. So they need polynomials to always have roots. So theorem 4. So we introduce this definition in a following or equivalent type situation. Let F be a field. Following conditions are equivalent. One, every non-constant f of x, f of x at the root. Two, every non-constant polynomial splits. A non-constant polynomial is irreducible. Irreducible. If and only if its degree is one. There is no non-trivial algebraic extension of F. And by non-trivial, let me point out that any field is an algebraic extension of itself. But I would considering F an extension itself to be what I refer to here as trivial. Every non-trivial, there doesn't exist a non-trivial algebraic extension. Yeah. And there is a field K and F such that F is algebraic over K. And every F of X, K of X, non-constant. Listen. Okay, so let me just kind of, I'll let this as an exercise of notes. Let's kind of walk through it somewhat. Oh, let me add Mark. So let me make off marks. Any field satisfying one hence all of these conditions is called algebraic. Um, Let me also point out that F can be F is the splitting field, the set of all polynomials in K. Um, So let's sketch this. Let's look at, 1 implies 2. So what do we have here? By the way, we're doing the hard way, yes, there's certainly 2 implies 1, doesn't it? What does 1 imply 2? So every polynomial has a root. We want to show that every polynomial splits. Let f of x be an f of x. I want to use the fact that f of x has a root to show that it splits. That was general. I don't think f of x be a monic polynomial because it's not. I'll just multiply by the inverse of the leading coefficient. The fact that this has a root means that f of x is x minus root 1 times f1 of x. Right? But then f1 of x has a root, right? Because this is also a polynomial. That's basically how it works, right? Every polynomial has a root, you just keep going until you exhaust it all. 2, every non-constant polynomial splits. Non-constant polynomials irreducible if only degree 1. Let me point out that degree 1 is always irreducible regardless, right? So no problem there. So really what we have to do is, assuming 2, we have to show this forward direction here. Suppose f of x is not constant. If degree of f is bigger than 1, then f is equal to x minus 12 u mod. Well, actually, this is not a if degree of f is m, then by hypothesis, by number 2, and then it has to factor this way, which implies m equals 1 if f is reduced. Right? Otherwise, it's got factors. 3 implies 4. So the irreducible polynomials are precisely ones at degree 1. Suppose that there is a non-trivial algebraic extension. So is non-trivial algebraic extension. Yeah. Let u, meaning e, not an f. Because of the fact this is irreducible, is a root of some f of x in f of x. Do I agree with that? Let me add this adjective. U is a root of an irreducible f of x in f of x. And But f of x is, let's make sure that f is mine, doesn't have to be the same as mine. Because I know that, my assumption is non-poly, oh, I'm doing two of them. Let me fix this. Let u be a root of the irreducible f of x. The degree f is fu over f, which is k. But by 3, k equals 1. Therefore, so let's see, I'm assuming not this. I'll show that we have a, yeah. Sorry about that. Let's try this again. So we're assuming that we have a non-trivial algebraic extension of f, and we're trying to show that there's a there's a polynomial of degree bigger than 1. So u is a root of this irreducible polynomial, and the degree of f is this, which is greater than 1. So there we go. F of x in f of x is irreducible of degree. So we've successfully shown not positive, not this means not this. Four plus 5. There are no non-trivial algebraic extensions of f. We want to show that there is a field k and f algebraic over k such that every f of x and k of x splits. Right. We have freedom to pick k. Somebody pick k for me in number 5. This one. Okay, left. All right. Certainly f is contained in f, check. F is algebraic over itself, check. So all we have to do is verify that every f of x and f of x splits. All right. So it suffices to show f of x splits. Well, they all. Yeah, there exists f of x that if not, then there exists an irreducible. E of x and f of x such that degree of g is bigger than 12, so equals a bigger than. So if there's some polynomial that doesn't split completely, it has to have an irreducible factor. Call it g at degree bigger than 1. And notice that F can be, construed as a subfield of Fx, G of X. Means a number. So, and I'll leave 5 and 5 for this exercise. On this but I'm not going to prove this next theorem. It actually requires some set theory, some getting into some stuff that I don't want to spend the time for right now. But I do need to record the theorem for you. Theorem 835. Any field K has an algebraic closure. And any two algebraic closures of K of X or K are K isomorphic. That is, there is an isomorphism from one field to the other that fixes K. Right. So, like I said, can anybody can tell me how would one construct such a thing? How would you construct, or what appeals to you is the way that you might construct the algebraic closure? You need to build something where all polynomials split. Well, the ambitious thing I think to do is if you want to construct a splitting field for K, what you do is you've got to make sure that every polynomial with coefficients in K splits. So why don't you take the splitting field of every polynomial, right? Now, there might be some problems with this, right? Because there's infinitely many polynomials over the field that can be problematic. And this actually, a careful proof, this involves the axiom of choice. And so I'm not going to, in a lot of kind of set theory, I'm not going to go into right now, but we can take this as given. Notice that, let me point out also that every polynomial, most of you at least know this very well from the folklore. If you have a polynomial with coefficients of rational numbers, then it factors into linear polynomials and complex numbers. Right? However, the complex numbers are super overkill to what the algebraic closure of Q is, right? The algebraic closure of Q you can construct by taking the splitting field of every polynomial Qx. Now, that construction is going to be countable, right? Because there are countably many polynomial coefficients in Q, and each polynomial has only finitely many roots, and a countable union of countable sets is countable. So the algebraic closure of Q is much smaller than complex numbers. Right? But this is, you might think about this. What this theorem says is you can also construct, for example, the algebraic closure of the field of two elements. Right? And that's going to be a very big field. Right? I mean, it's still going to be countable, but it's going to be far from finite. Spell separability, that's neat. Definition, let K be a field and F and KX irreducible polynomial. Irreducible. F is said to be separable if F factors into distinct linear factors in some splitting. Here's the important word here, distinct linear factor. And some. So when you go to the smallest field where this thing breaks down into factors into linear factors, then all the linear factors are distinct. Yeah. U and F. Well. Then an algebraic. So suppose we have an extension of fields. Let U be an element in F that's algebraic. So what do we know about this? It means it's got some minimum polynomial. We say U is separable. It's a separable element. If the minimal polynomial for U in X. So what is a separable element? It's an element whose minimal polynomial, minimal is important there, is a separable polynomial. And finally, F is a separable example. We have every element in F is separable. So let me point out, it's worth pointing out here that any field is separable over itself, right? Because if I have a field and I have an element alpha in this field, then its minimal polynomial is x minus alpha, right? Which is separable because it's already linear. Okay, I'm going to introduce a lemma next time, but I think this is a good time to quit. Any questions? Well, I hope you all have a great spring break, and I hope you be at the math club